day everyone. Now we will discuss the experiment 3 entitled Torques and Rotational Equilibrium of Rigid Body. So, the objective of this experiment is to apply the second condition of equilibrium, or the other name is rotational equilibrium, of a rigid body to a meter stick pivoted on a knife edge. Here, torque is defined as the tendency of the object to rotate, and the summation of all torque should be applying on the meter stick should be equal to 0 in order for the meter stick to experience an equilibrium. And the second objective is to determine the center of gravity of mass of the meter stick, and the mass of a known object by applying the known torques. And here, torque is equal to the force times the lever arm. And here, force should be perpendicular to lever arm. The unit of torque is Newton meter. And the third objective is for a given applied force needed to produce equilibrium, compare the theoretical predicted location of the force to an experimental determined location. So let's talk about torques and the second condition of equilibrium using the meter stick. As you can see in the picture, so we have here the meter stick. Since this is a regular object, usually in the regular object, the weight is applied on its center. So here, we will imagine that the force of gravity is applying on its center. This gravitational force is also called weight. So in a meter stick, we can find the position of the weight at 50 cm. And based on our discussion last time, we can solve for weight by solving its mass and its acceleration due to gravity. So if the mass should be in kilogram, we will multiply it to 9.8 meter per second squared. So the weight here, the unit of weight here is in Newton. What will happen if we will place one end of the meter stick on a knife edge? So as you can imagine, definitely the meter stick will tend to rotate. Based on what I've discussed a while ago, torque can be solved using the force times the lever arm. So first, we have to determine where is the pivot. Pivot is the point of the system where the object will rotate. Second, we have to find the formula first. So torque is equal to the force times the lever arm, and that lever arm should be perpendicular to the force. So it means, if the force is along y-axis, so that is going down, okay, so the lever arm should be in this form, okay, in that point. So first, where is the force in this system? So definitely the weight of the meter stick is a force, so that is our weight. And how will we find the lever arm? So that will be the distance from the pivot to the force applied. So that is a lever arm. We will look here. So the tendency of the object will rotate. So therefore, torque is not equal to 0. If we will replace the meter stick as a force, so torque now would be weight times the lever arm D. Let's have the first example. If the mass of the meter stick is 50 grams, what will be the amount of torque experienced by the meter stick? So here, we know that the mass is 0.5 kilograms. So we will convert the 50 grams to kilograms. So that is 0.05 kilogram. And the lever arm here is the distance from the pivot to the force. So that is 50 cm or 0.5 meters. And based on the formula what we discussed a while ago, so weight times the lever arm. And weight is equal to mg, so that is mass times gravity times the lever arm. And if we will place the given, so that is 0.5 kilogram times 9.8 meter per second squared times 0.05 meters, the answer is 0.245 Newton meter. So this one become Newton because this is kilogram meter per second. That unit is also equivalent to Newton, and that is meter, so that is Newton meter. So this is the magnitude of our torque, so definitely to indicate its direction. So for torque, there are two directions. It's either clockwise or counterclockwise. Now for this force, since this force is going down, the tendency of meter stick is to rotate in this direction, and we call this as clockwise. Our final answer for torque is 0.245 Newton meter clockwise, or CW. What will happen if we will position our knife edge on the center of the meter stick? So, this one. So, do you think our object or our meter stick will rotate? So, since the force is still there, so that is the weight of the meter stick, but the lever arm is equal to 0, so therefore, torque is equal now to 0. And that is the first case of the second condition of equilibrium. Now, if we will encounter a system that experiences a second condition of equilibrium, we can also use the first condition of equilibrium in this system by finding what is the force of the support. So, force of the support is just the force applied by the knife edge on the meter stick. Since the weight is going downward, so that is the pull of gravity, in order for the meter stick not to fall down or not to accelerate downward, the support will push it up, and there is an exerted force, which is what we call the F support, or the force of our knife edge. And in this case, we will use the first condition of equilibrium to find what is F support. And the first condition of equilibrium is just the summation of forces is equal to 0. So, in this system, we only have forces on Y. Hence, the summation of forces of Y is just equal to F support minus weight of the meter stick. So, since F of support is upward, so we determine it as positive. And the weight of the meter stick is downward, so that is negative of weight of meter stick. And since our system experiences an equilibrium, we can say that F support minus weight of the meter stick is equal to 0. And if we will transpose the weight of the meter stick on the other side, we can say that the force of the support is just equal to the weight of the meter stick. And if we will compute the weight of the meter stick from the previous problem, so that is 0.05 kilogram times 9.8, so that is 0.49 Newton, and that is also the F support. My question is, why we didn't include the force of the support in solving torque? So that is the F support. Since there is another force, so we assume that there are two torques applying on the system. But we know that F support times its lever arm, so the distance of F support to the pivot is equal to 0. So therefore, so that is equal to 0. So therefore, torque of F support is just equal to 0 or 0 Newton meter. Okay, so let's look for our second example. So if the mass of the meter stick is 50 grams and the pivot is at 30 cm mark, how much mass must we place at 0 mark to balance the system? The pivot is at 30 cm mark, the weight is still 50, and we have to determine how much mass we have to place at 0 mark to balance the system. So the summation of torque is equal to 0. Since we have two forces here, we have to determine what is the direction of our torque based on these forces. So if you will remember, so here is the pivot and this is the weight. So the tendency of the meter stick to rotate based on the weight of the meter stick is clockwise. And then for the unknown, the tendency of our meter stick to rotate, if the pivot is here, so the tendency of our meter stick to rotate due to the weight of unknown is what we call counterclockwise or CCW. If the tendency of the torque clockwise is just equal to the tendency of the torque counterclockwise, we can now have equilibrium. And here, the torque counterclockwise are positive and the torque clockwise is negative. So, torque CCW minus torque CW is equal to 0. That is the conventional direction of the two torques. And since this is equate in 0, so if I will move torque clockwise on the other side, we will just have torque counterclockwise should be equal to torque clockwise so that it will be in equilibrium. if the torque counterclockwise is not equal to torque clockwise, therefore, the summation of torque is not equal to 0. Let's solve now the problem. We have here M1 as our unknown mass, and we have M2 as our mass of the meter stick. And since this is torque counterclockwise, our torque counterclockwise is M1 times G, that is the weight of the unknown, times its lever arm D1. While M2, that is the mass of the meter stick, times the acceleration due to gravity, times D2, which is the lever arm of our meter stick. So how can we determine D1 and D2 first? So D1 is the distance from the pivot to the force applied. So here, if you will look on the meter stick, so this is 0 and this is 30 cm. So therefore, D1 is 0.3 meters. While for D2 is the distance from the pivot again to the force, which is the weight of the meter stick. So if you will look on the meter stick, so that is 10-20 cm. So D2 is 0.2 meters. And since we are looking for M1, we will derive this one. So that is M1 is just equal to M2G D2 divided by G D1. Here, we can cancel out G. Hence, our final formula is equal to M1 is equal to M2 D2 over D1. And let's substitute. So, as we substitute the given, the answer is now 0.033 kilogram. That is the required mass of our M1 to balance our system, or that is just 33 grams. The additional question is how much force exerted by the support. So we are looking for F support in this case. So from our previous example, we learned how can we solve for F support by using the first condition of equilibrium. And this will be also the case in this example, in which the summation of forces along Y will be is equal to F support, so that is going up, minus weight of the meter stick, so that is going down. And we have to add the weight of the unknown, which is also negative, and that is going down, so it's equal to 0. Since there are 3 forces in our system, so we have 3 forces also in our equation. And since this is in equilibrium, so that is equal to 0, so we can have this. And through this equation, we can easily determine the force of support by moving the weight of meter stick and weight of unknown on the other side. It will be just like this. And if we will solve now, so F support is just equal to weight of meter stick plus weight of unknown. So that will be M2G plus M1G. So that is 0.05 kilogram times 9.8 plus 0.033 kilograms times 9.8. So this one is 0.49 Newton plus 0.33 Newton. The F support now is 0.82 Newton. So the force of the support is just equal to the sum of the weight of the unknown and the weight of the meter stick. So let's proceed now to example number 3. So for example number 3, if a mass of 30 grams is hung at 80 cm mark, so that is weight 3, while its pivot is at 30 cm mark, how much mass must we place at 0 mark to balance the system? So again, we are asked to find weight 1. So here we are asked again to find M1, but we cannot answer here that the mass of M1 should be 30 grams because there is another weight that is hung on the other side of the pivot, and that is the weight 3 or a mass 3. Since the goal of this problem is to balance the system, we will use the second condition of equilibrium formula, in which torque counterclockwise is equal to torque clockwise. And here, weight of the meter stick and weight of the mass 3 is on clockwise direction, while M1 or the weight 1 is in counterclockwise direction. It means we will add the torque of the weight of the meter stick and torque of mass 3. Let's find the given first. So M1 is unknown, so that is what is asked in this problem. The lever arm of D1 is the distance from the pivot to weight 1, so that is 0.3 meters. And on the other side, the mass of the meter stick is also given, and its distance again from the pivot is D2, so this one. And its lever arm, the amount of lever arm is 0.02 meters. While for weight 3, which has the mass of 0.03 kilogram based on this given, and hence, since it is in 80 cm mark, we will get the lever arm of that. So from 80 cm mark to 30, so definitely the distance between pivot to our weight 3 is 50 cm. Okay, so let's proceed now to our equation. So this will be now the equation for this problem, in which we will have only M1 G D1 for the torque counterclockwise. The weight, so this one is the weight of the unknown times the lever arm of the unknown. While M2G is the weight of the meter stick times the lever arm of the meter stick, which is D2. And for M3G, that is the weight of the added mass here times the lever arm of that weight 3. And since we're looking for M1, let's derive. So it will be M1 is equal to M2G D2 plus M3G D3 over G D1. If you will look here, we can factor out G out of this equation. So by factoring out G, and there is G on here in the new denominator, so we can cancel it out. So what is left here is this one. So M1 is just equal to mass 2 times the lever arm 2 plus mass 3 times the lever arm 3 divided by the lever arm of 1. And let's substitute. So that is, these are the given for the meter stick. This is the given for the added mass, and this is the lever arm of our unknown. And hence, M1 now is 0.083 kilogram. How much force is exerted now by the support? So, since there are 3 weights now here, so definitely we assume that the force of the support is much higher compared to our example 1 and example 2. And since these 4 forces are just forces along Y, we now have the summation of forces is equal to F support, which is positive, minus weight of the meter stick, which is negative because it's downward, minus weight of M1, which is the unknown mass, minus the weight 3, which is the added mass. And hence, we can equate this equal to 0 because it follows the first condition of equilibrium. By moving all the variables of weights on the other side, we can have F support is equal to weight of meter stick plus weight 1 plus weight 3. And by substituting all the given, we can have 0.49 Newton plus 0.33 Newton plus 0.81 Newton. So that is the added weight of weight 3. So the F support is 1.63 Newton. That is now the force of the support. And lastly, let's have this example number 4. So if a mass of 60 grams is hung at 0 cm mark, so weight 1 now is not unknown, it's 60 grams, while the mass of the meter stick is 60 grams, so that is the mass, which is the weight of the meter stick. Where should you place the pivot to balance the system? So in this case, the unknown is the position of the pivot. Since the topic here is still the rotational equilibrium or the second condition of equilibrium, we will still use the same formula in which torque counterclockwise is just equal to torque clockwise. And this will be still the formula, so that is M1 G D1 is equal to M2 G D2. But definitely, we don't know what is D1 and what is D2. So, let's go to the meter stick and let's mark our meter stick. So, we will call X1 as the position of our weight 1. We will call X2 as the position of our weight 2. And we will call XP as the position of our pivot. So, that will be the position. So, to get D1, usually we will just subtract XP minus X1 since XP is higher than X1. So, that is XP minus X1. While for D2, since X2 is higher than XP, it will just be X2 minus XP. And let's substitute this equation to our D1 and D2. So it will be just like this. And to simplify our equation, we can remove the gravity since both of them have gravity. So it will be like that. As we remove the acceleration due to gravity, we can distribute M1 and also M2 in the equation. So that will be M1 XP minus M1 X1 is equal to M2 X2 minus M2 XP. And since we are looking for XP, we will move this M2 XP, negative M2 XP on the other side, while this one, M1 X1 to the other side. So, it will be just like this. So as we move this one, it will become positive. So, that will be M1 XP plus M2 XP is equal to, this is what is left on the other side. So, and as we move this one, M1 X1 on the other side, so from negative, it will become positive. So, plus M1 X1. Okay? And we can factor out XP since they are the same. So, it will be just like this. XP is equal times M1 plus M2 is equal to the same equation. And we can move it here. So, we can cross multiply it by this one. So, XP now is just equal to M2 X2 plus M1 X1 divided by M1 plus M2. So, this is the formula for getting the position of our pivot. And if we place our given, so that is M2. So, based on M2, that is the weight of the meter stick times its position. So, it is in 50 cm plus the weight of mass 1. So, that is said the weight of the mass 1 is 0.60 kilogram. And its position is at 0, so I put 0 meters divided by their masses. And hence, that is 0.025 kilogram meters because this will become 0 divided by 0.110 kilogram and cancel out kilogram. So the answer will be 0.2273 meters or 22.73 cm. So it means we will position our pivot at 22.73 mark cm. This one. Okay? So to check if this is the right answer, we have to prove that the amount of counterclockwise is just equal to the amount of torque clockwise. By using this formula, okay, so these are the givens. So D1 now, if we will go back, D1 is XP minus X1. So that is the position of the pivot is 22.73 minus 0. So that is also 0.2273. While the lever arm for D2, so we will subtract the position. So the position of the weight of the meter stick minus the position of the pivot is just equal to 50 minus 22.73 cm. So the answer is 27.27 cm or 0.2727 meters. And as we substitute the given, so this is the mass of weight 1, the gravity times its lever arm. This is weight 2, gravity, and this is the lever arm. Their answer is the same. So it means we got the correct position of the pivot in this example. So what we did in example number 4 is a way on finding the center of mass of a system. So the general equation to determine the center of mass is equal to So xcm is the center of mass along x is equal to m1x1 plus m2x2. If there are many given masses, so you will just add it, divided by m1 plus m2 to mn. So if there are so many masses, you will just add it, and still you will find the position of the center of mass along x. Now, if our meter stick is in vertical position, we will just also do that. So instead of x1, we will use y1, y2, yn divided by still the masses. Now, but we have to note, okay, I have to note that all positions, so that is x1, x2, and xn, y1, y2, and yn, should be measured from the origin. So if this is the meter stick, we will place it in an axis as if the end of the meter stick is at 0. So from our previous problem, x1 is at the position of 0, and the position of the meter stick is at 50 cm. So again, we have to place all the masses as if it's in an x-axis. We will measure all the positions of these masses from the origin to its mass. And if we will find now the center of mass, that is also as if the position of our pivot. Okay, now let's go to the experiment proper. So let's talk about the procedure. Now, the first thing you have to do is to find the mass of the meter stick and the center of gravity of the meter stick. So here, that is in kilogram and that is meter. So if you will check the video, you can see there, the first part of the video will tell you the mass of the meter stick and its center of mass. So the center of mass of the meter stick alone. Okay, so we will do 3 procedures for this experiment. So part 1, we will determine the torque due to 2 known forces. For part 2, we will determine the torque due to 3 known forces. And for part 3, we will determine the torque of the meter stick mass by torques. For part 1, we are finding the torque due to 2 known forces. So we will find the position of x2. So please look on the video of the experiment to find x2. From its position, you will also determine where is the pivot in that experiment. So you will get the lever arm D1. So this is the position of the pivot based on the experiment to weight 1. And for D2, you will also determine the position of your weight 2 based on the experiment in the video to the pivot. Okay, so the pivot here is always on the center, so the weight of the meter stick is not included since the weight of the meter stick is on the pivot. And please compute the torque counterclockwise by multiplying mass times gravity times the lever arm, and also compute for the torque clockwise by multiplying the mass 2 times gravity times lever arm. And since this is a system of equilibrium, rotational equilibrium, the torque counterclockwise should be equal to torque clockwise, and you will get the difference of that. Okay, so please use this formula to find the percentage difference of your 2 torques. So that is percentage difference is equal to the absolute, so it means it's always positive. Torque counterclockwise minus torque clockwise divided by the average of the 2 torques. So to get the average, that is torque counterclockwise plus torque clockwise divided by 2. And your answer should be placed here. For procedure number 2, there are 3 masses now. So still the pivot is in 50 cm. So it means the weight of the meter stick doesn't involve in this problem. So this is weight 1 and the lever arm is D1. And the position of our weight 1 is 0.1 cm. Weight 2, so this is weight 2 and the position of that is 75 cm. And our mass 3 is this and the position of that is unknown. Please watch the video to determine what is the position of your weight 3 and its lever arm is D3. So again, you have to compute the lever arm. So it means D1 is the distance from the pivot to weight 1, D2 is the distance from the pivot to weight 2, and D3 is the distance from the pivot to weight 3. And so based on their position, so you have to add the torques of weight 1 and weight to determine the torque counterclockwise. Well, for the torque clockwise, you will just get the torque of weight 2. And again, we know that torque clockwise and torque counterclockwise should be equal. Hence, we will get the percentage difference. Here, we will use the same percentage difference we have in procedure 1. And please place your answer here. And for the last procedure, we will have determine the mass of the meter stick by torque. So this is an example of getting the center of mass, in which here, position M1, so that is here at point 1 meter, you have to determine the mass 2 and the position of 2 in the video. So that will be that one. And the pivot is not at 50 cm. We will include the weight of the meter stick and its position. So you have to determine the center of mass by applying the center of mass formula, which is xp is the position of the pivot, x1 is the position of weight 1, x0 is the position of the meter stick, and x2 is the position of your mass 2. Okay, so we will further discuss this one. So this is the formula for getting mass O, or the mass of the meter stick. So you will derive it. So this will be the mass O is just equal to this equation. Please follow the position. And finally, to complete our table, so the yellow one will be the data you will get from the video. You will solve for D1 and D2 based on the picture above, which is D1. This one, so D1 is just XP minus X1. D2 is just X2 minus XP. That will be how to solve lever arm. And since we are looking for MO, so this is the formula. And okay, please do not forget this is support position. This is not XO, this is XP. Do not forget to place the position of your support in this part. Okay, and we will now get the percentage error, in which we will compare the mass of the meter stick based on the digital balance we measured before, minus what we have computed here, divided by what is measured, absolute, that is always positive, times 100, and place your value here. So as you complete the part 3 of the procedure, please also complete page 52, answer the questions 1, 2, 3. And please do not forget all the computation. Please attach another page or another bond paper. So I hope that is clear. And so after this, please watch the video for our experiment.